Florian, and he will tell us about values of the Ramanujan tau function. Go ahead, Mike.
I will try. Give me a second here. Let me see. Can people see that?
Yes, we can see that very well.
Okay, fantastic. So, well, thanks very much for the kind invitation to both to Claude and Florian. I guess I'm the last speaker, not of the session, maybe the whole conference. So we're going to go out with a whimper rather than a bang. But I'd like to, maybe we should all give a round of applause to our organizers first. So thanks so much, Florian and Claude. So this is, keep going forward. This is joint work with Adela Gerga, Vandita Patel, and Samir Siksek. As is traditional for me, I will try to skip over lots of details. If I make some really horrific mistakes, then I'll attribute those to Samir. So I'm talking today about values of the Ramanujan tau function, and it's going to be a sort of pessimistic, rather negative talk in that I will be talking about values the Ramanujan tau function doesn't take, rather than a more optimistic, positive talk about values it might take. So again, the Ramanujan tau function, I think everybody probably knows what it is, sort of classical modular form with a Q expansion I've given at the bottom here. So we've got coefficients that start off 1, minus 24, etc. And it's remarkable for many reasons, being studied for more than 100 years. And we know a great deal about it, and there's a great deal about it we don't know still. So again, it's as part of a much more general framework about Fourier coefficients of modular forms. That's how one would look at it nowadays, but it is again conjectured by Mordell that this is actually a multiplicative function, conjectured by Ramanujan, pardon me, proved by Mordell, and pretty easy if you apply Jacobi's triple product formula. You can sort of do this expansion to convince yourself that you have the mod 2 congruence I have in the middle of the page, which tells you sort of right off that tau of p is always even. And in particular, tau of n is going to be odd just when n is an odd square. So, so we'll come back to that. That's sort of necessary for what I'm going to be talking about later. So again, certainly one of, if not the most outstanding open problems about the tau function is whether it's actually equal to 0. And that's still an open problem. It's very hard to get traction on that problem, it seems. I should point out there's a lot known about their arithmetic nature. A lot of these things on average, or assuming GRH, we basically understand somewhat the number of prime divisors, the growth, things like that. Somewhat, I can be more precise because as a sort of consequence of much more general results at Deline, then we do have a bound again on tau of p, so it grows polynomially at most in p, prime p. And in the other direction, again, part of a much more general series of conjectures, we actually expect that we have polynomial lower bounds. So it's really growing like p to the kappa, where kappa is somewhere between 4.5 and 5.5. That's our expectation. And so if this conjecture is true, which note is a very strong conjecture, it's much stronger than just saying tau of p isn't 0, or isn't 0 very often, it should tell you that this tau function, at least on primes, takes a given fixed integer at most finitely many times. So now, again, there's very little we can say about tau of p, very little that's known sort of unconditionally. But if we restrict attention to values of the tau function that are actually odd, then of course we're looking at a very thin sequence of n. As I mentioned before, n has to be an odd square. So in that case, there's actually much more machinery we can bring to bear. So in that case, a classic result of Murty and Tarlac-Shoury using lower bounds for linear forms and logs shows that tau of n actually grows like a power of log, and here the exponent's a positive constant. So why I got interested in this was a talk by Ken Ona was talking about some recent results of his joint with many people and a number of his students on establishing non-existence results for various odd values of tau of n. So prior to that, we had results that tau of n is not plus or minus 1. And then Ken and various co-authors and students produced results about tau of n not being an odd prime up to 100, an odd integer sort of up to 100. So this, in a sense, they're making it's an effective result of Murty, and Shorey, and making it explicit and actually solving things with that. So what I want to talk about today are things sort of, they look sort of similar, but the techniques are a bit different that go into them. So these are if you like, non-Archimedean analogs of this result of Murty, and Shorey. So what we have is so if you assume, I guess, that n is an odd square, so that tau of n is actually odd, then we can actually show not just that that tau of n grows, but that the greatest prime divisor of tau of n grows. And we have this fairly absurd looking statement on the right hand side here. It's a log of n, which Dan Shanks famously said many years ago, goes to infinity with great dignity. I think that's true. And on the bottom, it's quadruple log. And this is sort of artifice of the method. Probably the truth is something more like log, but it's no better than that. So it's in the neighborhood of that would be my guess. And it's not even necessarily true. This is, we have this lower bound unless Lamer's conjecture fails. If Lamer's conjecture fails, and it's not just an artifice of the method, if Lamer's conjecture fails, then this lower bound is not true. In fact, there's no lower bound you can have that's a function of n, as I'll show in a second. So I'll show literally right now. So if Lamer's conjecture is false and you have a p for which tau of p is 0, then tau of p to the 2k is actually a power of p, plus or minus a power of p. And so the greatest prime divisor is just p. And that does not depend upon k. And so Lamer's conjecture, we have various heuristic reasons to believe that it's true. But we don't know it. We do know that if you're going to find a counterexample, it's not small. So, and there's quite a bit of interesting work that goes into actually computing the Ramanujan tau function. And so certainly into verifying this result of Derricks, Van Hoij, and Zhang. Okay. So what we really prove, and again, this is sort of fairly clear, if you have a multiplicative function, you can really look at it on prime powers, is that we basically have a growth in the greatest prime divisor of tau of p to the m of order log of that. And then when you have that, you put that together. If you have this result, if this is the truth, then the truth when you go to tau of n is the log of this, basically, that you can cook up. And so we basically have this, we separate into a couple of cases if m is small and if m is not so small. And the methods, as you'll see in a second, really do have to be somewhat different. So that's sort of in one direction, and just one would think, well, okay, can you make that explicit? And the answer is, well, we don't really, because it's sort of painful, but we can apply rather different techniques to solve these kind of things very explicitly. So we can handle, if you like, the equation at the bottom here. So this is, again, we're making the assumption here, again, I'm not writing out, but n, of course, has to be an odd square for this to have any chance of holding. But then it can't be an odd square whose greatest prime divisor is smaller than 13. And should mention there's earlier work of Florian with some co-authors who did the same result. I think it's without the 11. And I'll mention a little bit that the 11 makes it, in some sense, it goes from hard to quite a bit more difficult. And I'll mention what happens if you try to push this a bit further. But this is done explicitly, and it's rather different techniques. So the techniques involved for this result are much closer to the things that Ariel Picchetti was talking about earlier. So just to point out, a little aside, so Ramanujan tau function does take prime values. Well, what we believe the smallest one to be, this is not a proof, the smallest one we know of is this one I've got here, tau of 251 squared. That's the smallest n for which tau of n is prime, not necessarily the smallest value, a prime value it takes. The suggestion, I think this actually Sarah made this pretty explicitly, is that there should be infinitely many such values. Tau should be prime infinitely often, but not very often. So it's sort of some sort of log growth kind of condition. And what we've done is a rather more modest thing of showing that, well, it's not a prime power for any odd prime up to 100. Okay, and we could probably push that to 1,000 if we were suitably motivated, and frankly we're not, because it seemed a good place to stop. Okay, so again, two really separate techniques. So the first of them is really has a lot of basis in that the argument of Murty and Shorey is just that we have to, where they appeal to lower bounds for linear forms and complex logarithms, we have to appeal to bounds in non-Archimedean logarithms as well. And the second, the explicit one with 2s and 3s and 5s and q's and stuff like that, that's really using Frey curves and some computational tricks associated with them. So, and again, just to point out that this is all easily generalizable to some class of coefficients of new forms with even weight, trivial character, and you need some sort of local condition at 2. So they have to be, the coefficients have to be even, basically. And this is just the case of k equals 12. Okay, and this all goes through, but we just restricted it to this. So it looks like an unrelated aside, but just to mention, we heard discussion earlier, I think, of Luca sequences and things like that. So a Luca pair, again, it's a pair of algebraic numbers that show up, if you like, as through their sum and their products as coefficients in some polynomial, a quadratic polynomial for the integers with small restraints put on it. We've got a non-zero discriminant, and we get a corresponding Lucas sequence. So lots of things come out of this that are very familiar. And these sequences we know a fair bit about. And the main result we want to pull out of this is that these sequences have what are called primitive divisors. So it's a beautiful result of Bilot, Aron, and Vucce, that you go far enough out, and far enough is not particularly far. This is a special case. They prove this for more general Luca-Lamer sequences. You go far enough out and you get what's called a primitive divisor. So it's a prime that didn't divide the discriminant and didn't divide the earlier terms. So why that's useful to us, sorry to go back, is that if I want to say, if I have a member of a Luca sequence and I want to say, hey, when is this thing a power of 17, for example, then the point is that it's going to show up, the 17 is going to show up somewhere, and if you look a second time, it has to get a new prime divisor. And so it can't kind of show up twice. So this is a way to kind of sort of home in on what element of the sequence could possibly lead to a power of 17, for example. And so this is a term that goes back 100 years or so, calling thing the rank of apparition is the first place that a given prime shows up. So the rank of apparition for 17 is the first place it'll show up in the sequence, the index, if you like, in a sequence, if you like U1, U2, U3, etc. And the point here is that it's something, and this goes back to at least to Carmichael, that this is very easy to figure out what it is. If my prime is 17, then the index, oops, let me go back here, the index, place where it first shows up is either the 17th place or some index dividing 16 or 18. So at most, the 18th place is the first place it shows up. And then by the primitive divisor theorem, you won't be able to get all powers of 17 anywhere past that. So it kind of, this sort of structure will give you, if we can get a Lucas sequence to show up here, this will give you an upper bound upon how far we have to search. Okay, well, what happened here? And so the point is that if you look at the sequence, you fix a prime P, you look at the sequence of tau of powers of P, then this is essentially a Lucas sequence. And the key point to this is this identity, which again goes back in conjecture to Ramanujan and proof to Mordell. So it's a recursion that tells you how to generate these things. And that sort of thing, it's like anything else, like a Fibonacci sequence, the recursion guarantees that you get a sequence of this shape. And so for us, if Lamer's conjecture fails, then you get a thing that isn't a Lucas sequence. It's sort of a degenerate thing that just goes back and forth between zeros and powers of P. But if Lamer's conjecture holds, then there's not that many P's that can show up. And once you scale by them, you get a Lucas sequence. So you basically get a Lucas sequence if Lamer's conjecture is true. And I'll point out that the scaling, you have to scale anytime you get P dividing tau of P. And this happens. And again, this happens sort of most likely infinitely often, though it's hard to prove this. Okay. So for us, what it turns out, this recursion does more. If you play around with it, the recursion lets you actually write tau of p to the m. So the elements in the sequence, you can write each of them. So if m is odd, you actually get a tau of p shows up. That's the tau of p to the delta there. And if m is even, it doesn't show up. So delta is 0 or 1. And the rest of it is some binary form in tau of p and p to the power 11. And the binary form has degree the integer part of m over 2. So for instance, I give an example here. Tau of p to the 5th is tau of p, and then it's a quadratic form in tau squared of p and p to the 11. And that's much more general thing. And that's a sort of thing, again, once you got this recursion formula, it's very easy to prove this inductively. And so why we have to separate the cases here is that for small m, this form has degree at most 2. It's degree 1 in the first couple of cases and degree 2 in the next couple. And quadratic forms and linear forms behave very differently from binary forms to degree at least 3. So you don't have 2A's theorem, 2A Mahler's theorem. You don't have results like this that give you finiteness on representations of integers with a bounded support. So you have to treat these differently. And in each case, by manipulation, you can actually rewrite what you get for tau p to the m as being divisible by some square minus some fixed integer in 1, 2, and 5 times some 11th power. It's not always the same 11th power, but it's something like this. And the point is that this y squared minus dx to the 11, this is something that you can actually say something about its prime divisors. So this, if you like, if you fix the prime divisors of this, it's a question about asking about S integral points on a genus 5 curve. So there are finiteness statements for this, and lower bounds for linear forms and logs tell you that then that the greatest prime divisor that grows at least like log of the entry. Okay, so that's a sort of an effective statement that lets you get that. And for the higher degree, then, so for example, in the case of m equals 6, here delta 0, then you just get this cubic. It's a cubic form, again, in p to the 11 and tau squared of p. And you're asking, if you basically say, hey, when is that cubic form divisible by 2, 3, 5, 7, and 11, then just powers of those, then that's what's called a 2A Mahler equation. And those are, there are sort of classical results for that. We can plug in, and with a bit of work swept under the carpet, you get lower bounds of this fairly unpleasant looking shape log over triple log. And then you simply apply this to the largest prime power divisor, and this gets you triple log over quadruple log, which is painful. And yes, if you go throw in an n that's 100 digits, I think this thing is still less than 2, but nonetheless, it eventually goes to infinity. Okay. So for the explicit results, okay, then what we have to do for this kind of thing is we have these various congruences. So the classical congruences for Manderson conjecture, we have congruences modulo what I've written here, but also mod 691. The 691 is less valuable for our purposes, but we have these congruences. And so what we can do is reduce the possibilities of the exponents using this. And in fact, by a lot. We basically show that the only things that can show up in large numbers are the 11s. Everything else is very easy. Then if we appeal to the primitive divisor theorem, that says, gosh, if you've only got 2, 3s, 5, 7s, and 11s, then primitive divisor theorem says if m gets big, you keep picking up new primes. And so primitive divisor theorem will give you an absolute bound on m, and it's a small one. Then for the ones that are greater than or equal to 6, you've got 2A Mahler equations you have to solve. And for the ones that are less than or equal to 5, you've got to handle them a different way. And that's where almost all the work goes in for us. So in particular, if you apply this, you actually end up getting these tremendously strong constraints upon the exponents of 2, 3, 5, and 7, that 3 of them are 0 and one of them is either 0 or 1. And to these things, you can write down these Frey curves, and these are nice. They're even nicer than the ones that Ariel talked about, in that they're not just Q curves, they're actually defined over Q. And what you have, sort of classical thing here, is that you actually have congruences between the Fourier coefficients of these Frey curves, Frey-Elguars curves, if you like, and between particular weight 2 cuspal nu forms at particular levels that are actually bounded here. The delta i's, the exponents of the 3 and the 11, are either 0 or 1. So this is at worst 32 times 33. So it's some fairly small space to work in, very easy to work with. And because of the 11 that's showing up, that's related to our weight for the Ramanujan tau function, we get congruence as mod 11. And we get this for every prime L if we exclude basically 2s and 3s and 11. And so what we can do then is sort of sieve using this local data. So here we've got the ALEP. These are Fourier coefficients of a particular Frey curve. We don't know the curve exactly, but we do know it is a rational 2 torsion. So these are all even integers, and they're in a particular bound due to Weil bounds. And these things, CL, these are actual algebraic integers in some number field, but it's all very controlled because we can actually write these things down. They're a particular weight and level, so we can just write these things down, and we can just simply check what this gives us. And so if we sieve just using relatively small primes, we end up with one of 2 conclusions. So either this thing started out, remember, there couldn't be any 2s and 5s and 7s due to Ramanujan congruences. We either end up in the case where beta equals 1 and there's no 11s, or we end up in the case where beta equals 0 and the exponent of the 11s is divisible by 11. So in the first case, okay, what did I write here? Okay, maybe this is in the, yes. So in the first case, you simply go ahead and write that equation out. It's like y squared minus x to the 11 equals plus or minus 3. You factor this over q adjoin root 3 or root minus 3. I can't remember one of them. You can rule out locally. And then this leads to a degree 11 2A equation. And this is something that, while not fun to solve by hand, is well within the range of what you can handle computationally these days, say by Magma, and you can solve it. And the sort of rather depressing, sad punchline is that the only solution is 1, 0, and that leads to p equals 1, a contradiction. So that's, if you like, the kind of easy case. And the slightly harder case, well, if the exponent of 11 is divisible by 11, then we actually have a solution to the equation x to the 11 plus y to the 11 equals a square. And a beautiful result of Darman and Morel solving what was called Denish's conjecture is that there's only trivial solutions to that. So just to finish up, okay. So for this one, again, we avoided 2A Mahler equations. We avoided having to deal with these. But when we want to do these things, if we do this with, instead of having small primes on the left-hand side, very small primes, we allow primes up to 100. We actually can't get around the 2A Mahler equations. So for example, in the case q equals 83, we have to solve this particular one, which is not so bad. But we have to solve this one, which is a wee bit worse. So degree 20. But it's one of the sort of nature of the beast here that the real bottleneck in solving these things is finding a system of fundamental units. And it turns out that these are very, very, very nice binary forms. So again, I mentioned that the 2A Mahler solver, which is something that Samir and Adela have been building, have built, is that it requires this sort of class group information. And normally, again, if the degree is large, this just isn't practical. So probably degree, well, even degree 13 or 17 would be a real pain right now. But in our case, the number field is really, really simple. So the number field really is just this, it's the sort of real subfield of Q zeta M. So this is the, M through T unity. And that's true for all of these. So the drops out of this is very, very nice. And this is incredibly easy computationally to handle as these things go. So just to finish up then, so the bad news, probably one could include 13 on the right-hand side. This would be painful, but possibly doable. 17 would be genuinely a bit much, I think, just to do the modular form computations. And the bottleneck, perhaps surprisingly, is actually handling the tau of p squared and the tau of p to the 4th. So these are the cases where our binary form is degree 1 or 2. So you're not really doing 2A Mahler stuff here, but you're doing something else. And in that case, that's bad. But it turns out we really can go a lot further if we just look at tau of p to the m for a little bit bigger m. So remember this tau of p to the 6th, this was just some cubic form. So if we basically say, I'm going to do some cubic form and I'm going to put in lots of primes. Actually, we can go a bit past this now. I think we can get to 43 or 47. And this is more of an advertisement for the strength of the new 2A Mahler machinery that Adela, Samir, and also Raphael von Kanel and Benjamin Matschke have built, are in the process of building, should be publicly available relatively soon. So I'll stop there and thank you very much.